Hi students, as we have finished calculus part, now we are getting back to leftover part of the material, that is geometry. In this video, we are going to talk about conic sections. You can simply call them conics. Okay, what are conic sections? Conic sections are two-dimensional curves that are obtained as a section when we cut a double right circular cone with a plane. I will explain what the double right circular cone shortly. First, let me give examples of conic sections that you are already familiar with. They are the following: point, straight line, pair of intersecting straight lines, circle. These are four examples that you already studied. Now I am going to give three more two-dimensional curves as an examples of conic sections that we are going to study in upcoming material. They are parabola, ellipse, hyperbola. You might have heard these names, but you have not studied them in detail. Now let me explain what the double right circular cone is. Okay, when a straight line meets the vertical line at a fixed point at an angle alpha, and if we rotate straight line about the fixed vertical line keeping alpha constant, then the surface generated is called double right circular cone because it has got two cones joined at fixed point V. It has got circular base which is perpendicular to fixed vertical line. That's why the name double right circular cone. Here the fixed vertical line CD is called axis of the cone and the rotating line AB is called generator of the cone. And the fixed point which is intersection of generator and axis is called vertex of the cone. And the angle between generator and axis is called vertex angle. We denote it by alpha. The two cones that you see here are called naps. One above the vertex is called upper nap and the one below the vertex is called lower nap. If we cut this double right circular cone with a plane that makes beta angle with the axis of the cone, then the intersection is going to be a two-dimensional curve. This intersection of the plane with a cone takes place either at the vertex of the cone or any other part of the nap. In the following context, alpha denotes the vertex angle, beta denotes the angle that cutting plane makes with the axis of the cone. Here I am considering double right circular cone with a vertex angle alpha equal to 30 degrees. When plane cut the nap at the other than the vertex of the double right circular cone, we could mainly end up with one of the three following situations. One situation is when alpha less than beta. Here we have alpha equal to 30 degrees and we have taken cutting plane so that beta equal to 50 degrees. So we have alpha less than beta. In this case, the intersection of the cone and plane, as you can see, a closed curve which is called an ellipse. There is a special case here. If we have alpha less than beta and beta equal to 90, that is when axis of the cone is normal to cutting plane, we get a special ellipse called circle. Other situation is when alpha equal to beta. Here we have alpha equal to 30 degrees and we are using cutting plane so that beta equal to 30 degrees. So we have alpha equal to beta. In this case, the intersection of cone and plane, as you can see, is an unbounded open curve, something called parabola. In each of the above situations, the plane cuts entirely across one nap of the cone. The third situation that we could end up with is when beta is strictly less than alpha. Here we have a alpha equal to 30 degrees and we are using cutting plane so that beta equal to 20 degrees. So we have beta strictly less than alpha. In this case, the intersection of cone and plane, as you can see, it consists of two unbounded open curves, which is something called hyperbola. Unlike the previous cases, in this case, plane cuts through the both the naps. Now, if we let the plane cut through the vertex of the double right circular cone, the ellipse that we used to get when alpha less than beta will now be a point. And the parabola that we used to get when alpha equal to beta will now be a straight line. And the hyperbola that we used to get when beta less than alpha will now be a pair of intersecting straight lines. Here, the point, straight line and pair of intersecting straight lines are called degenerate conic sections, whereas ellipse, parabola, hyperbola will be called non-degenerate conic sections. You can think point as a degenerate case of ellipse, straight line as a degenerate case of parabola, and pair of intersecting straight lines as a degenerate case of hyperbola. Conic section can also be defined as the locus of a point moving on a plane such that its distance from a fixed point and a fixed line are in constant ratio. It can be proved that these two approaches to define a conic section as a plane section of a cone and as a locus of point are equivalent. We will not prove this fact here as it is beyond the scope of this material. We are going to use second definition to study conic sections because definition is analytic in nature rather than geometric. Now, let me state analytic definition of conic section. Here is the definition. A locus of points which moves in a plane such that distance from fixed point and a fixed line in the plane are in a constant ratio is called conic section, or you can simply call conic. Here the constant ratio is denoted by E. Here the fixed point is called focus and we denote it by S, and the fixed line is called directrix and the constant ratio is called eccentricity. This is a fixed point focus, this is a fixed line directrix, and we are talking about locus of point such that SP by PM equal to E. Here SP is distance from this focus to this point and PM is perpendicular distance from this point to this directrix line. Okay, if P is a point on a conic with eccentricity E for given focus and directrix, we should have SP equal to EPM. Okay, fine. The type of the conic that we are going to get will be completely characterized by the eccentricity value E. Okay. Now let me state what values of E will give what conics. Okay. Here, if E equal to 1, then the conic you get is called parabola. If E less than 1, then conic is called ellipse. There is a special case here. When E less than 1, E could be 0 also, right? When E equal to 0, that ellipse will be a circle. Next, if E greater than 1, then conic is called hyperbola. If you want to connect this eccentricity E with our first approach to define a conic section, that is conic section as intersection of double right circular cone and the plane, okay, this E will be equal to cos beta by cos alpha, where alpha is the vertex angle, beta is the angle that cutting plane makes with the axis of the cone. I will not prove it here, but I will make sense of it. We know we get a parabola when alpha equal to beta, right? If alpha equal to beta, then obviously cos alpha equal to cos beta. So then E value cos beta by cos alpha value will be 1. So this makes sense. We know we get an ellipse when alpha less than beta, right? Here 0 less than or equal to alpha, beta less than or equal to pi by 2. Okay. So we should know something about cos function. Cos is a decreasing function at 0 value 1, at pi by 2 0. So from 0 to pi by 2 cos is a decreasing function. So for alpha less than beta, cos alpha will be greater than cos beta. So that implies cos beta by cos alpha value less than 1. So in this case, E value cos beta by cos alpha value less than 1. So this makes sense. And we also know we get a circle when alpha less than beta and beta equal to pi by 2, right? If beta equal to pi by 2, what happened to the numerator here? Cos pi by 2 by cos alpha. That is E, right? So that is 0 by something. That is 0. So this also makes sense. Next, we get a hyperbola when beta less than alpha. Obviously, these are like this. So again, since cos is a decreasing function, we know that cos beta should be bigger than cos alpha. That will give you cos beta by cos alpha greater than 1. So in this case, see, E greater than 1, this also makes sense. Fine. So the analytic definition of conic section is going to be locus of points which moves in a plane such that distance from fixed point and fixed line are in a constant ratio E. This E is something called eccentricity. Okay, if E equal to 1, we get a parabola. If E less than 1, we get an ellipse. In particular, if E equal to 0, you get a circle. If E greater than 1, then you get a hyperbola. Fine. Now let me introduce some important terms in the context of general conic section. The first one is axis. The straight line passing through the focus and perpendicular to the directrix is called axis of the conic. Let's say this is your focus and here is your directrix. Okay, the line passing through the focus and perpendicular to the directrix is called axis. This is going to be your axis. Okay, the next one, vertex. The point of intersection of conic and axis is called vertex of the conic. For some conic we may have a more than one vertex, so in that case we should say vertices. For example, for a parabola you will have one vertex, for ellipse and hyperbola you will have a two vertices. Okay, let me show you here. Let's say this is your focus and directrix and this is the axis. So this is your, let us say, conic parabola. In that case, the intersection of axis and the conic, this is what? This is a point, okay? This is going to be a vertex, okay? So in the case of ellipse, okay, let's say this is your ellipse. So the axis is going to be this one. So this is going to meet the conic in 2 points. Let's call it A1 and A2. These two are going to be vertices. Fine. Okay. Next. Focal chord. Any chord passing through the focus is called focal chord of the conic. For example, so any chord passing through the focus. So this is the one chord. Okay. Let's say AB. This AB chord passing through the focus. This is going to be focal chord. There could be more than one, so we can draw other one also, like this is another one, CD. Okay, this is also going to be focal chord. Okay, fine. Any chord passing through the focus is called focal chord. Simple. Next, double ordinate. A chord that is perpendicular to axis is called double ordinate of the conic. For example, so any chord, okay, for example, let's say, let me draw this chord. Okay, this is a one chord which is perpendicular to axis. This is double ordinate. Okay, so in this case, let's say, let me draw this one. Okay, this is a chord perpendicular to axis, so this is also double ordinate. Next, latus rectum. The double ordinate that is passing through the focus is called latus rectum. This is simply focal chord which is also double ordinate. Okay, see, this is the focal chord, but this is not perpendicular to axis of the conic. But so this is another focal chord which is perpendicular to axis of the conic. That means, so this block chord, let's say AB, okay, this is going to be focal chord also double ordinate. So this is an example of a latus rectum. Okay, next, center. The point that bisects every chord of the conic passing through it is called center of the conic, if exist. For some conic, the center may not make sense. For example, for a parabola, center do not make sense, but for ellipse and hyperbola, center makes sense. Okay. For example, if I take a ellipse, okay, so this is the axis. So let us say vertex 1, vertex 2. If you take the midpoint of these two vertices, let's say C, this will work as a center, because if you take any chord through it, it will obviously bisect, right? Any chords. That's why for ellipse center makes sense. But if you work with a parabola, then center do not exist. Okay, center do not exist. Fine. Okay. Now let us derive general equation of the conic section. Let the focus S equal to alpha beta and directrix is Lx plus My plus N equal 0. Okay. So if I take Px1, y1 be any point on conic, then by definition we should have Sp equal to Epm, where E is the eccentricity of the conic, right? Okay, what is Sp? Sp is the distance from this focus is to point x1, y1, here S is alpha, beta, and the Pm is perpendicular distance from this x1, y1 to this directrix Lx plus My plus N equal 0. So this Sp going to be under root x1 minus alpha whole square plus y1 minus beta whole square E times that Pm is perpendicular distance from this x1 y1 to Lx plus My plus N equal 0. This is going to be mod Lx1 plus My1 plus N by under root L square plus M square. If you square both sides, you will end up with this one, x1 minus alpha whole square plus y1 minus beta whole square equal to E square times lx1 plus my1 plus n whole square by l square plus m square. So therefore, the locus of point P is going to be x minus alpha whole square plus y minus beta whole square equal to e square times lx plus my plus n whole square by l square plus m square. Okay, I'm not simplifying this equation because this equation in terms of given focus alpha beta and given directrix lx plus my plus n equal 0. Okay, so this is the equation of the conic with the eccentricity E whose focus is alpha beta, directrix is lx plus my plus n equal 0. Okay, now the equation of axis of this conic is going to be m times x minus alpha minus l times y minus beta equal 0. Because what is the axis? So this is the axis. Line passing through focus alpha beta and perpendicular to directrix. Directrix is what? Lx plus my plus n equal 0. What is the slope of this? Slope of this directrix going to be minus L by m. So the slope of the axis must be what? M by L. So the line passing through alpha beta having the slope m by L going to be what? Y minus beta equal to m by L times x minus alpha. So that will give you this equation. So this m times x minus alpha minus L times y minus beta equal 0 will be equation of the axis of the conic whose focus is alpha beta, directrix Lx plus my plus n equal to 0. Okay. Actually, if we further simplify this equation, you will end up with a general second degree equation in x and y. Okay, because you will have some x square term, you will have some y square term, you will have some xy term, there will be x term, y term and constant term. So if you expand both sides, this equation will turn out to be a general second degree equation in x and y that look like this. Okay, ax square plus 2hxy plus by square plus 2gx plus 2fy plus c equal to 0. So a general second degree equation x and y will represent a general conic. Okay, so this is the general conic equation. Okay, which for a b h g f c, if you write equation like this, that will be a conic equation which could be anything: point, pair of straight line, circle, hyperbola, parabola, ellipse, stuff like that. Okay, fine. So fine. In particular, the general equation of the parabola with a focus alpha beta and directrix Lx plus my plus n equal 0 will be this: x minus alpha whole square plus y minus beta whole square equal to Lx plus my plus n whole square by L square plus m square. We obtain this equation by simply taking eccentricity E equal to 1 in the general equation of the conic that we obtained in the previous slide. Because for parabola, eccentricity E equal to 1, right? That's how we obtain this equation. Okay. If you further simplify this expression by expanding left hand side, right hand side and regrouping the terms, you will end up with a general second degree equation like this. Okay. So this is going to be a x squared term, this is going to be a y squared term, this is a xy term, this is x term, y term, constant term. Feel free to verify this. Interesting thing is, here I group the second degree terms x squared term, y squared term, xy. Okay, remaining all are constant term and first degree terms. Okay, so these second degree terms will complete square because here you see m square x square l square y square minus 2lmxy. I can write mx minus ly whole square. Okay, so this general equation of the parabola can always be expressed like this: mx minus ly whole square plus some x term 2gx plus 2fy plus c. Here, this one you can think like a g, this one you can think like a f, this all constant you can think like a c. Okay, so the second degree terms in the general equation of the parabola always complete square. Okay, that is something special about the general equation of the parabola. Okay, so let me make a note here. Second degree terms in the general equation of the parabola forms a perfect square. Okay, fine. Recognition of conics. Just looking at general conic equation, is there a way to decide nature of the conics? That means we want to know if that equation represents parabola or hyperbola or ellipse, stuff like that. Answer is yes. Just by computing two quantities in terms of the coefficient of the second degree equation in x and y, we can actually decide nature of the conics. Okay. A general conic equation going to be a second degree equation x and y like this: ax square plus 2hx5 plus by square plus 2gx plus 2fy plus c equal to 0. Here this whole second degree expression we denote by s. Okay. So this equation can be recognized by computing two quantities in terms of these coefficients ah, b, g, f, c. The first one is ABC plus 2FGH minus AF square minus BG square minus CH square, which we denote by delta. Another one is AB minus H square. Looking at these two quantities, we can actually decide nature of the conic. Okay, I'm just going to state the condition and nature of the conic when that condition holds. We are not going to prove them here. Okay. When delta non-zero and AB minus h square equal to 0, you get a parabola. But when delta equal to 0 and AB minus h square equal to 0, you get a degenerate case of parabola, that is straight line. When delta non-zero and AB minus h square positive, you get an ellipse. But when delta equal to 0 and AB minus h square is positive, you get a degenerate case of ellipse, that is a point. There is a special case here. When this AB minus h square positive, you may have a case h equal to 0 and a equal to b. In that case, if delta non-zero, it will be a circle. Otherwise, again, if delta equal to 0 and h equal to 0, a equal to b, then again you will get a point. Next, when delta non-zero and AB minus h square is negative, then you get a hyperbola. But when delta equal to 0 and AB minus h square is negative, you get a degenerate case of hyperbola, which is pair of intersecting straight lines. Okay, so this is how computing these two quantities delta and AB minus h square, we can actually decide nature of the conic. Okay, fine. Now one thing we can observe here, note, we get a non-degenerate conics for s equal 0 when delta non-zero. What are non-degenerate conics? Parabola, ellipse, hyperbola. And we get a degenerate conics for s equal 0 when delta equal 0. Degenerate conics are line, point, and pair of straight lines. Okay, fine. In this chapter, we are going to study only parabola. The next chapter, we will be studying ellipse. Then we will be studying hyperbola. Okay, fine. Now we want to study parabola in detail. To study nature of any curve, we want to pick its equation in simplest possible form. Now we want to derive such an equation for parabola, which we are going to call standard form equation of parabola. Okay. Now let us consider the parabola whose focus is a comma 0 and the directrix is vertical line x plus a equal to 0. Here a comma 0 for a positive means, so this focus is sitting on x axis positive side. Okay, we are so picky in choosing focus and directrix to make equation simple. Okay, now Now, as a comma 0 is the focus and directrix is this vertical line x plus a equal to 0, then axis of this parabola must be x-axis because this line must be passing through a comma 0 and perpendicular to this vertical line. So it must be x-axis. So in this case, the axis of the parabola are going to be x-axis. Now let us try to derive equation of this parabola whose focus is a comma 0 for a positive and directrix is x plus a equal to 0. Okay, let x1 y1 be any point on the parabola. Then from the definition of the parabola we should have this sp equal to pm. Okay, because here eccentricity equal to 1, right? So we should have sp equal to pm. Then what is sp? Distance from this point s to p, it's going to be under root x1 minus a whole square plus y1 minus 0 whole square, and pm is going to be perpendicular distance from this x1 y1 to this directrix. It's going to be mod x1 plus a by under root 1 square plus 0 square, which is simply going to be mod x1 plus a. Okay, if you square both sides, then you will end up with this x1 minus a whole square plus y1 minus 0 whole square equal to x1 plus a whole square. So this gets simplified to left hand side, you will have x1 square plus a square minus 2ax1 plus y1 square. The right hand side will be x1 square plus a square plus 2ax1. As you can see, x1 square cancel, a square cancel. What you have is y1 square equal to 4ax1. Okay, so we got this one, y1 square equal to 4ax1. Therefore, the locus of point px1 y1 going to be y square equal to 4ax. Okay, so this is the equation of the parabola in simplest possible form. Okay, we know that for general parabola equation, second degree term should form a perfect square. But in this case, there is only one second degree term which is square only, so no problem. Now remark, if the focus S lies on directrix, then locus is going to be straight line passing through focus and perpendicular to the directrix. This is a degenerate case of parabola. If this focus S sitting on directrix only, then this locus of point SP equal to PM will be a straight line passing through the focus but perpendicular to the directrix. Okay, I'll show you that. Okay, let me take focus to be point on x-axis a comma 0, and let me fix directrix to be x plus 1 equal to 0, which is a vertical line. Okay, now so for this focus and directrix, the locus of point P such that SP equal to PM should be a parabola as long as this focus is not sitting on directrix. Okay, so this SP equal to PM will give you under root x minus a whole square plus y minus 0 whole square equal to Pm is mod x plus 1 by under root 1 square plus 0 square. That should give you x minus a whole square. If you take square both sides, y square equal to x plus 1 whole square. Okay. This should give parabola as long as this focus not sitting on directrix. So my claim is that if this focus sitting on the directrix, this equation will give you line, straight line. Okay, because this is a directrix. If S is here, for only points in the plane, SP equal to PM happens only for points on this axis. This is going to be x-axis. If I take any P here, if this is S here, SP this one and M also. If I take the foot of the perpendicular from P to this directrix, that also going to be yes. So obviously SP equal to PM. That happen only for points on this x-axis. So in that case, the locus is going to be straight line. Okay, fine. Let me show you this. See here. So this is the equation. I'm taking a equal to 2 here. If I take a equal to 2, the SP equal to PM equation is going to be x minus 2 whole square plus y square equal to x plus 1 whole square. Okay. And here the red line is directrix x plus 1 equal to 0. Here the focus is 2 comma 0 for a equal to 2. Okay. If I change this A, you see what happens. Once A is sitting on the red line, it will become line. See? So you are getting parabola all the time except when S is sitting on the red line. That's when you are getting straight line. That green curve is going to be a straight line, which is the x-axis. You see that? Once S is on, see, I can even stop this one. See, let me take a equal to minus 1. So now you see, if I take a equal to minus 1, that green curve happened to be this x-axis, straight line. Okay, the line passing through the focus and perpendicular to the directrix. But for any a other than this minus 1, you will get a parabola. You see. So when focus lying on the directrix, the locus of P such that SP equal to PM going to be straight line. This is the degenerate case of parabola. Next, okay, parametric equation. For this particular parabola whose focus is a comma 0 and directrix is x plus a equal to 0, the parametric equation going to be x equal to 80 square, y equal to 280. For any t from minus infinity to infinity, this point 80 square comma 280 will be point on this parabola y square equal to 4ax. You can simply substitute, it will satisfy. You can see. So here 280 whole square equal to 4a, what is x here? 80 square. You see now left hand side same as right hand side. 4a square t square actually equal to same 4a square t square. That means for any t from minus infinity to infinity, this point 80 square comma 280 will be point on the parabola y square equal to 4ax. Okay, not only that, Any point on this parabola y square equal to 4ax in fact will be in this form for some choice of t, at square comma 2at. Okay, I can show you that. For example, this point x1 y1 will be in this form x1 equal to at square, y1 equal to 2at for some choice of t. Okay, what I do is let me draw tangent at this point. Okay, so what will be the slope of the tangent? You know, if you differentiate this one, you get 2y dy by dx equal to 4a. That implies dy by dx is going to be 2a by y. So the slope at x1 y1 going to be equal to 2a by y1. So the slope of this tangent going to be what? 2a by y1. Okay. Now let me say this tangent makes some angle with this y-axis. Let's say theta. If this is theta, then this also going to be theta, and here we have a 90 degrees. So this must be pi by 2 minus theta. So in terms of the definition, the slope of tangent must be slope of tangent must be tan of this angle pi by 2 minus theta. Okay, so that must be equal to cot theta, that equal to, now let me take t equal to tan theta. See here, tan range is from minus infinity to infinity, so t can be any number from minus infinity to infinity. If I take my t to be this tan theta, then here the cot theta will be 1 by tan theta. So that implies, so this is going to be 1 by t. The slope of the tangent equal to 1 by t. Actually, what is the slope of the tangent we got? 2a by y1. So 2a by y1 equal to 1 by t. That implies, so y1 equal to, if you cross multiply, you get 2at. Okay, this is what my y1. If you substitute y1 equal to 2at here, what you get? 2at whole square equal to 4ax1. This will be 4a square t square equal to a 4a x1. Here this 4 cancel, this a and this square cancel. So we got x1 equal to at square. See, any point in fact in this form at square comma 2at for some t belongs to R. Okay, that's why this x equal to at square, y equal to 2at for t from minus infinity to infinity is going to be parametric equation of this particular curve y square equal to 4ax. Okay, so for this equation y square equal to 4ax, parametric equation going to be x equal to at square, y equal to 2at. Here t vary from minus infinity to infinity. When t equal to 0, the point will be 0, 0 here. As you move t from 0 to infinity, the point moves here, okay, on upper part of the parabola. Okay, as t moves from 0 to minus infinity, the point moves on lower part of the parabola. Okay, here we consider the parabola y square equal to 4ax for a equal to 2, and we take a point at square comma 2at. So for t equal to 0, as you can see, the point P is at a 0, 0. Now you see how this point moves on parabola as t vary from 0 to infinity as well as 0 to minus infinity. You just see this. When t positive, the point will be on upper part of the curve. When t negative, point will be in lower part of the curve. Okay. So this y square equal to 4ax curve open right side. It's an open unbounded curve, but it's open right side. Here, few more things we want to observe. So this curve is symmetric about the x-axis. Okay, and here so the vertex is going to be 0 0, right? Intersection of this axis and the parabola y square equal to 4ax going to be 0 0, and the tangent at the vertex is this one, it's y axis. Okay, okay, fine. Now let's look at all other standard form equations of parabola. This is the equation that we just considered, y square equal to 4ax. We derived this equation by taking focus to be a comma 0 sitting on positive x-axis and directrix to be vertical line x plus a equal to 0. Okay, so here the equation is y square equal to 4ax. Vertex of this parabola is 0 0 and focus is a comma 0 and directrix equation is x plus a equal to 0 and axis is x-axis whose equation is y equal to 0 and tangent at vertex is y-axis whose equation is x equal to 0 and parametric equation of this parabola is x equal to 80 square, y equal to 280. Okay. Next, this is the parabola whose equation is y square equal to minus 4ax. You will derive this equation when you take focus to be minus a comma 0 sitting on negative x-axis, directrix to be vertical line x minus a equal to 0. Okay, that's how you derive this equation y square equal to minus 4ax. Fine. Here the vertex is going to be 0 0 again. Focus is minus a comma 0 and directrix is x minus a equal to 0, which is a vertical line, and axis again x-axis whose equation is y equal to 0 and tangent at vertex is y-axis whose equation is x equal to 0. Now this time parametric equation going to be x equal to minus 80 square, y equal to 280. Fine. Next, this is a parabola whose equation is x square equal to 4ay. You will derive this equation by taking focus to be 0 comma a, which is sitting on positive y-axis, and directrix to be horizontal line y plus a equal to 0. Here the vertex is going to be 0 0 and the focus is 0 comma a. Directrix equation is y plus a equal to 0 and axis is y-axis whose equation is x equal to 0 and tangent at vertex is going to be x-axis whose equation is y equal to 0. Here the parametric equation is going to be x equal to 280, y equal to 80 square. Okay. Next, this is the parabola whose equation is x square equal to minus 4ay. Okay. You will derive this equation when you take focus to be 0 comma minus a, which is sitting on negative y-axis, and directrix to be horizontal line y minus a equal to 0. Here the vertex is 0 0, focus is 0 comma minus a, directrix equation is y minus a equal to 0 and axis is again y-axis whose equation is x equal to 0, and tangent at vertex going to be x-axis whose equation is y equal to 0, and here the parametric equation going to be x equal to 280, y equal to minus 80 square. As you can see, this y square equal to 4ax parabola open right side, y square equal to minus 4x parabola open left side, x square equal to 4ay parabola open upward, and x square equal to minus 4ay parabola open downward. As you can see, these two, y square equal to 4ax, y square equal to minus 4x, these two parabolas are symmetric with respect to x-axis, and x square equal to 4ay, x square equal to minus 4ay, these two parabolas are symmetric with respect to y-axis. Fine. Remark: for any x positive, there are 2 points on the parabola y square equal to 4ax, p, p dash. Here p is x comma 2 root x, p dash is x comma minus 2 root x. These are the 2 points on the parabola for given x positive. Here you can see this p, p dash perpendicular to axis of the parabola. Hence this p, p dash will be double ordinate through p. Okay. If you are interested in length of the double ordinate p, p dash, it's going to be 4 root x, because this length is 2 root x, this also 2 root x, the total is going to be 4 root x. Okay. In particular, if you are interested in length of the lattice rectum, what is the lattice rectum? Double ordinate passing through focus, right? So this L dash going to be lattice rectum. This length of the lattice rectum going to be 4a, because here we have to take x equal to a, right? So if I take x equal to a, here what you get? 4 root a times a, that is 4a. Okay, the length of the lattice rectum is going to be 4a. For general parabola, the a is going to be distance between vertex and focus. Okay, so this distance is going to be a. Okay, so length of the lattice rectum for any parabola always equal to 4a. That a is what? For general parabola, distance between the vertex and focus. That is the a. Okay, fine. Now we are going to look at transformed equations of standard form equations of parabola when we shift vertex 0, 0 to the point h comma k. Okay, let us consider the parabola y square equal to 4ax. Okay, here we have a focus at a comma 0. Directrix is this vertical line x plus a equal to 0. Vertex is 0, 0. Now, if we shift this vertex 0, 0 to the point h comma k, then the transformed equation of y square equal to 4ax will be this one. Okay, this dotted parabola whose equation will be y minus k whole square equal to 4a times x minus h. Okay, now for this parabola, axis is going to be this y minus k equal to 0 horizontal line, which is parallel to x axis, and vertex is going to be h comma k, and the focus is going to be a plus h comma k. This is the focus. Okay, and tangent at vertex is going to be vertical line x equal to h, which is parallel to y axis. Okay, and directrix of this parabola is going to be x minus h plus a equal to 0. Okay, fine. So this y minus k whole square equal to 4a times x minus h is the equation of the parabola with the vertex h comma k and axis is parallel to x axis. Fine. Now let us look at the all transformed equations of standard equations of parabola when we shift vertex 0, 0 to point h comma k. Now we are going to look at equations of parabola with vertex h comma k and axis is parallel to coordinate axis. Okay, here is a parabola whose equation is transformed equation of parabola y square equal to 4ax when vertex 0, 0 shifted to h comma k. Here the equation of this dotted parabola going to be y minus k whole square equal to 4a times x minus h. Vertex going to be h comma k and the focus is h plus a comma k and directrix is x minus h plus a equal to 0, which is the vertical line, and axis is y equal to k, which is the horizontal line, and tangent at h comma k going to be this vertical line x equal to h. This h comma k is vertex of this parabola. Okay, and the parametric equation of this dotted parabola going to be x equal to h plus 80 square, y equal to k plus 280. Okay, x equal to h plus 80 square, y equal to k plus 280. Here t anything from minus infinity to infinity. Fine. Okay. Next. So this is the parabola whose equation is transformed equation of parabola y square equal to minus 4ax when vertex 0, 0 shifted to h comma k. Here the equation is this y minus k whole square equal to minus 4a times x minus h. The vertex going to be h comma k and the focus is going to be h minus a comma k and directrix is this one x minus h minus a equal to 0 and axis is y equal to k line, horizontal line, and tangent at h comma k going to be this x equal to h, and parametric equation of this dotted parabola going to be x equal to h minus 80 square, y equal to k plus 280. Okay, next. This is the parabola whose equation is transformed equation of x square equal to 4ay when vertex 0, 0 shifted to h comma k. Okay, here the equation is this x minus h whole square equal to 4a times y minus k and the vertex is h comma k and focus is h comma k plus a and directrix is y minus k plus a equal to 0, this horizontal line, and axis is this vertical line x equal to h. Okay, this is the line, and tangent at vertex going to be horizontal line y equal to k. Okay, this is a tangent at h comma k, and the parametric equation of this dotted parabola going to be x equal to h plus 280, y equal to k plus 80 square. Okay, next. This is the parabola whose equation is transformed equation of x square equal to minus 4ay when vertex 0, 0 shifted to h comma k. Here the equation is x minus h whole square equal to minus 4a times y minus k. Here the vertex going to be h comma k and the focus is going to be h comma k minus a and directrix going to be this y minus k minus a equal to 0 horizontal line and axis is going to be this line vertical line x equal to h and tangent at h comma k going to be this one, this horizontal line y equal to k, and the parametric equation of this dotted parabola going to be x equal to h plus 280, y equal to k minus at square. Okay, so these are the equations of parabola with the vertex h comma k and axes are parallel to coordinate axis. Okay, there are four types. Fine. Note the equation y minus k whole square equal to 4a times x minus h can be expressed in the form x equal to ay square plus by plus c for some a positive. That is, here we are writing x equal to some quadratic function of y. Okay, let me show you this. If I expand left hand side, I will have a y square plus k square minus 2yk equal to 4ax minus 4ah. Okay, so then 4ax I can write y square minus 2yk plus k square plus 4ah. So if I bring the 4a this side, I can write x equal to 1 by 4a y square plus minus k by 2a times y plus k square by 4a plus h. So as you can see, now this is a, so this is b, this is c. Now x equal to ay square plus by plus c form. Here the a is positive, right? Here we know a is positive, so the 1 by 4a must be positive. So we managed to express this one as x equal to ay square plus by plus c for a positive. So here this equation we can write as like x equal to some quadratic function of y. Okay. Similarly, the equation y minus k whole square equal to minus 4a times x minus h can be expressed in this form x equal to ay square plus by plus c for a negative. This time the a will be negative. Okay. Next, similarly, the equation x minus h whole square equal to 4a times y minus k can be expressed in this form y equal to ax square plus bx plus c for some a positive. Here y equal to a quadratic function of x. We are writing y equal to some quadratic function of x. Okay, this can be expressed this way. In the same way, x minus h whole square equal to minus 4a times y minus k can be expressed in the form y equal to ax square plus bx plus c for a negative. Okay. So therefore, the equation of the parabola whose axis is parallel to x-axis will be in this form. X equal to ay square plus by plus c for some a non-zero and bc all are real number. Okay, but a must be non-zero. Okay, fine. If a positive, this parabola will open right side. If a negative, this parabola will open left side. Okay. Next, the equation of the parabola whose axis is parallel to y-axis will be in this form. Y equal to ax square plus bx plus c. Again here a, b, c are real numbers, a non-zero. Again, if a positive, this parabola will open upward, and if a negative, this parabola will open downward. Okay, fine. Parabolic curves. For real numbers a, b, c, where a non-zero, the equation y equal to ax square plus bx plus c and the equation x equal to ay square plus by plus c both always represent parabola. So they are called parabolic curves. Okay. First, let me have a close look at this first equation y equal to ax square plus bx plus c. If I take a common, then I can write y equal to a times x square plus b by 2a x plus c by a. Now let me multiply and divide by 2 here. So I am writing here y equal to a times x square plus 2 times b by 2a x. Now let me add and subtract this b square by 4a square so that I will be able to complete square. Okay, now here, so this part will complete square. So let me write a times x plus b by 2a whole square and minus of here this b square by 4a square plus we can write b square minus 4ac by 4a square. Okay, fine. So we have y equal to a times x plus b by 2a of whole square minus b square minus 4ac by 4a square, as it is same thing. Okay, now if I take this a inside, then I will have y equal to a times x plus b by 2a whole square. So this square will cancel, then I will have minus of b square minus 4ac by 4a. Okay, if I take this minus of b square minus 4ac by 4a this side, so then I will have, so I can write like this x plus b by 2a whole square equal to 1 by a times y plus b square minus 4ac by 4a. Okay, this is how we can express this equation y equal to ax square plus bx plus c. Okay, let me call it 1. So this 1 we can write like this 1 can be written as, okay, x minus of minus b by 2a. Okay, this plus b by 2a I am writing minus of minus b by 2a, x minus of minus b by 2a whole square equal to 4 times 1 by 4 mod a. Here a positive, so I am replacing a with a mod a. So 4 times 1 by 4 mod a times y minus of, here this I am writing, minus of 4ac minus b square by 4a. Now this look like, x minus h whole square equal to 4a times y minus k. Okay, or if a negative, you can also write like this. If a negative, then a you can replace with minus mod a. So this equation I can write x minus of minus b by 2a whole square minus 4 times 1 by 4 mod a times y minus 4ac minus b square by 4a if a negative. This one look like, x minus h whole square equal to minus 4a y minus k. We know this is the equation of the parabola with the vertex, what is h comma k here, minus b by 2a comma 4ac minus b square by 4a, and whose axis will be parallel to y-axis. So we can say that this one represent parabola with a vertex minus b by 2a comma 4ac minus b square by 4a, and whose axis parallel to y-axis. Okay, fine. So this y equal to ax square plus bx plus c is a equation of the parabola whose vertex set, minus b by 2a comma 4ac minus b square by 4a, and axis will be parallel to y-axis. Okay, next. Similarly, x equal to ay square plus by plus c can be expressed as follows: y plus b by 2a whole square equal to 1 by a times x plus b square minus 4ac by 4a. Let me call it 2. Okay. Now These two can be written as follows. Okay, if a positive, then a we can take as a mod a, so we can write like this: y minus of minus b by 2a whole square equal to 4 times 1 by 4 mod a times x minus of 4ac minus b square by 4a. So this one look like y minus k whole square equal to 4a times x minus h. Okay, if a negative, then a we can write as a minus mod a. So in that case, the same expression too we can write like this: y minus of minus b by 2a whole square equal to minus 4 times 1 by 4 mod a times x minus of 4ac minus b square by 4a when a positive. Now this one look like y minus k whole square equal to minus 4a times x minus h. In both cases, our a happened to be 1 by 4 mod a. Okay. So, looking at this equation, we can tell that, so here, what is h comma k? H comma k going to be 4ac minus b square by 4ah. K will be minus b by 2a. So, looking at this equation, we can tell that, so these equations represent parabola with a vertex 4ac minus b square by 4a comma minus b by 2a, and whose axis will be parallel to x-axis. Okay, so x equal to ay square plus by plus c always represent a parabola with a vertex 4ac minus b square by 4a comma minus b by 2a, and axis will be parallel to x-axis. Fine. Okay. Focal distance. The distance between focus of parabola and point on the parabola is called focal distance of that point. Let's find out focal distance of point on one of the standard parabola y square equal to 4ax. Okay. Let px1 y1 be a point on the parabola y square equal to 4ax whose focus is a comma 0. By definition of focal distance, the focal distance of the point P must be equal to SP, that is, distance from this focus to that point. And from the definition of the parabola, we should have SP equal to PM. PM is what? Perpendicular distance from this point to this directrix. Okay, and you can see that PM actually equal to PN plus NM. See? So this PM total we can see as Pn plus Nm. Okay. Now you can see this Pn equal to x1 and Mn equal to A. See, as you can see, this equal to A because here this is a point minus A comma 0. This is 0 comma 0, right? So this distance is going to be A. And since this is a point x1 y1, okay, so this distance must be equal to x1. So as you can see, the Pn is going to be x1 and Nm is going to be A. So this focal distance SP going to be x1 plus A. As you can see, so the focal distance of point P equal to x1 plus A. Therefore, for a point x1 y1 on the parabola y square equal to 4ax, the focal distance of P going to be x1 plus A. Okay. Okay, let me stop here. Thank you.